interest rates बता दिए हैं वो interest rate is working now.
Yes.
Alright, so let's do it again. Recall that what we did last time, we said that we have a model for movement of our underlying assets actually. So our model is dealing with two kind of assets. One is risk-free and other is risky. The risk-free, the movement of the dynamics of risk-free asset can be given as like this. If the initial work is P naught, the work at time one is going to be that we just simply multiply it with 1 plus R, which is going to kind of give you the feature value of the P naught, which is denoted by V1. And the risky assets, the initial work is S naught. We are assuming that for S naught, there are only two possible trajectories that it can take. So either this value can go up and can attain a particular number which is S1U, and or it can go down and it can attain a value that's 1D. Okay, it's like a very unrealistic, simplistic possible model. But as the mathematical recipe is that every model begins with something very simple, and then you keep on adding the ingredients to make it a rich model. And then we try to answer some of basic questions. Number one, is this model a good model? By a good model, I mean that is it a viable model? And by viability, I mean that does this movement of a stock allow you to create an arbitrage opportunity or not, free lunch or not. So if it isn't allowing you to create arbitrage opportunity, okay, that's what we want, then we're going to say that it's a model. And a sufficient condition or necessary and sufficient condition for the viability of the model is that it should, like these three values, okay, should satisfy the inequality. In other words, the future worth, it's like a future worth of S naught should lie between these potential values. Okay. So if this inequality, holds, then you're going to say that your model is a good model, it's a viable model. But if this is violated at an instant, then you're going to say that you have an opportunity. Okay, so that's what we tried to the next thing that we try to answer the next question that we try to answer was that imagine I have a derivative. So in other words, I am kind of roughly betting on this movement of the stock. I don't know what's going to happen in the future. Okay. But for example, I am kind of quite optimistic that price will go up. Okay, and that can allow me to make some money. Okay. So it's like I'm betting on the upward movement of the stock actually. I equally bet on the downward movement of the stock as well. So in other words, a derivative by a financial derivative or a contract. Okay. Look that you guys have read the chapter 1 of the book, okay, which kind of gives you essential background. If you haven't, go and check it out again. So mathematically, a financial derivative is nothing. It's just basically a function depending on the stock, the underlying asset, okay, which we denote by, for example, omega. So when I'm basically saying that D is depending on omega, and omega is Right, this omega should be what potentially U and RD, okay? Roughly it's some function of basically what we call, S1. Okay, that's what it's till that. In other words, you are saying that it's a financial derivative, okay, which is, potentially can give you this much amount of money at time one, okay? But we don't know that whether you're going to get this much money or not, because things can go against our, okay, against our expectation, and it's kind of a worthless thing. Anyways, financial derivative is nothing; it's just simply a function of the underlying asset. Okay, and then and one of the examples that we discussed in detail was what we call option. Option. Okay. Now, option is a very interesting kind of a derivative. Okay, like a financial contract, which can in some situations get rid of the risk actually. Like, it can reduce the risk actually. If you are potentially exposed to the risk, then you can control that risk potentially by buying or selling an option, taking a short position or a long position if the options active. Okay. Now, since this option is kind of allowing you, okay, to hedge the risk at time one, okay. The fundamental question that we tried to answer was that, okay, what should be the worth of this option at time zero? In other words, that how much premium should be. So if you are a buyer of an option, that how much premium you should pay to the the seller of the option, not the person with a long position. Or if you are a seller of the option. If you are the other way around, then how much you should charge the other party as a premium. So it's like that premium, we essentially say that is basically what we call the fair price of that derivative. Zero. The second question that we try to answer is that in a viable model, so imagine if your model is a good model, okay, it does not contain any arbitrage opportunity, what must be the price of the derivative P at time zero. We try to answer. And we try to answer this question in two ways. Okay, one of the way was answer that what is the fair price of the derivative at time zero. So the answer of this question, can be given in two ways. One way, price derivative is that I can price it through what we call replicating portfolio. Okay. Replicating portfolio. Only with the probably it's better that I must use it. So, in order to answer the question that what should be the fair price of a derivative that is allowing you to hedge your risk, different things at time one, the answer to this question can come in two ways. There are two methods to basically do the fair pricing of a derivative, and one method was to ask the question that is D attainable? Is it an attainable derivative or not? Okay. That is that can we find a portfolio investment in bonds and a stock, underlying asset, X represents bonds and investment in bonds, and Y represents your bonds and shares, such that at time one you can attain the value of this derivative by this portfolio. Okay, and what is going to be the value of this portfolio? It's like a V1 value x comma y, and that value is going to be x1 plus y s1 of omega. So in other words, we are saying that is there an investment strategy, okay, whose value is equal to what? The payoff of the derivative, value of the derivative at time. Okay. So if you are able to find such x and y's, you're going to say that your derivative is attainable. And once you have such x and y, okay, which can attain the value of the derivative at time one, the same portfolio can be used to compute the price of the derivative at the time 0, and it's because of what you call the law of one price, that A, if I have two, kind of objects, financial objects, okay, roughly, depending on the same, underlying asset, okay, and their values agree on time one, then law of one price say that their value should agree on the time zero as well. Okay, so this means that, so if I have a portfolio x and y such that its value can attain basically what the derivative d, that the derivative at time one, then the price or the premium of the derivative d, okay, that should be charged by the person with the long position is going to be what? Is going to be just simply compute the value of the portfolio at a time 0, which is going to be x1 plus ys0. Okay, so if the model is given to you, that means that you can easily compute price of the derivative. Okay, now since we have two omegas, okay, how can I find? Apparently, this looks like one equation actually, but it's not one equation, it's two equations actually. With this omega, so one equation you can get when omega is u, and second equation you can get when omega is v. Solve that system of equation, you're going to get x and y's, and those x and y's can give you basically what premium for the derivative. Okay. So this was one method, basically, method to price the derivative by why, this theory is an important theory. We discussed it last time. So imagine I have a monster, which is the stock, okay, which no one understands that why it moves randomly. we can do is that we can kind of make models for the movement of randomness. Unfortunately, we don't have a fully successful model for that. You have models, but those models work under certain assumptions, but they are not as good. They are not as good as capture basically that monster. Right? So once you have this monster, and obviously, if you are making an investment based on this monster, so the values of your investment are going to go up and down as well. So what we want to do actually, so we want to do is that we want to save our investments. Okay. So one way to save our investments are to basically at least be able that if you are, for example, in certain trouble, then you should be able to meet with that trouble. Okay, and you should be able to meet with your obligations. Okay, if you have any obligations, using what what you call the derivatives are. So derivatives are, so since you are making risky investments, derivatives are the tools that allow you to hedge the risk. Get rid of the risk or minimize the risk. So that's what essentially philosophy. And then, so that's a one way to basically price it. The second way to price the derivative is what you call through risk neutral probabilities. Okay? And how we're going to do it, how we did it basically last time was discrete time. So we know that our model is viable. In other words, it's a good model. It does not contain any free opportunity if and only if the future value of the stock lies between these two potential values that the stock can take possibly in the future. Okay. And then we can be a bit more mathematical. We can say that, okay, this means that 1 plus R S naught is a number and it belongs to this interval. Okay? It belongs to this interval. And since this interval is a convex set, okay, then somehow this number can be written as kind of a weighted average. Okay. Convex combination of so in other words, I can, since the interval, open interval is every open interval is a convex set, so there exists a Q between 0 and 1 such that this 1 plus R S naught can be written as what do you call Q S1 of V plus 1 minus Q S1 of U. So you can kind of write it as the convex combination of S1 of D and S1 of U. In other words, that's a kind of an equivalent condition of the viability of the model that you want to model. And this is true if and only if I can write this as S naught can be written as, for example, S1 bar of V plus 1 minus Q, S1 bar of U. And what is this now? Now, I mean, if you see the model, okay, so it's like a S naught, S1 U, and S1 D, okay. For me, S1 is a kind of a random variable. Okay, it's a random variable. Okay. So it's what you call the map from omega into R. That random variable. R plus actually by other option. Okay. Now, if it is a random variable and it can take potentially these two values, okay, the question is that what does this expression represent? So if I treat these Q, which are numbers between 0 and 1, as probabilities, then this is nothing but we are saying that if the expectations of random variable S1 bar agrees with S1. S0, you're going to say that your model is a viable model. Okay? Now why this equation makes sense actually? Try to understand it more explicitly, and then I will try to answer basically what. So I'm just recalling what we did last time. Okay. One thing. Imagine x is some quantity. Okay. And it's a quantity at time, for example, 0. Okay, since we have 2 gates up to this time. If you multiply this quantity with, for example, this 1 plus r, so this new value, which you get basically what, by multiplying this value with 1 plus r is going to give you what you call the future value of x. Future value of x on next date actually. So if this date is 0, then it is going to give you what you call the future value for x. And if you divide this quantity by 1 plus r, okay, fine. If you're not, if you instead of dividing a quantity by 1 plus r roughly, okay, so it's going to give you the value of x not at the current date but the previous date. So imagine that's a value at time 1, you discount it, you're going to get its value actually what? X is r at time 0, for example. Okay. Now just think about it. So if I have a value s1, okay, so it's a value at what time? 1. And then you discount it. You got its value at time 0. And then you are saying that, okay, computed expectation. So you are saying that what is the expected value of the S1 at time 0 should agree with the original stock value. In other words, there shouldn't be a difference between these two quantities. Okay. There shouldn't be a difference between these two quantities. So this makes sense actually. These are not two strange objects. So that's expected value of S1 at time 1, and that's really the value of the stock at time, not time 1 but time 0. That's really the stock value at time 0 and then Roux value. Okay. So if your model is a good model, you should be always able to find such a cube. Okay. In other words, this inequality must hold. Okay. So that's kind of an equivalent condition for the viability of the model. Okay. Now, okay, I was not interested in this part actually. Repeating it, I'm forced to repeat it because I want to give you the context as well. Okay. But the key thing that we tried to answer is that using this probability measure. Now, what's this Q actually? So for me, this Q is probability measure actually. Probability measure, okay. A probability distribution. You're happy to say, okay, where the Q1 is Q and Q2 is 1 minus Q.
Sir, what's the difference between S1 and S1 bar?
There is huge difference between us. So S1 is the value of the stock at time 1, while S1 bar you are discounting it by factor 1 plus R, so it's going to give you the value of S1 roughly at time 0.
Discount.
But since you are not sure about what exactly is going to be S1, okay, what exactly is going to be S1, so therefore you are involving expectation. The expectations. I know that what is going to be the S1. So whatever is going to be S1, but the expected value of S1 or S1 bar should linearly be equal to S1. Okay? And this probability measure I discussed in detail last time is what we call the risk neutral probability measure. Okay? And I can quickly recall that why this is a risk neutral probability measure. It's a risk neutral probability measure because if you compute the expected returns on a stock, discounted the stock, you're going to get what you call the deterministic. In other words, if I compute the expected value of return on a stock, okay, I'm going to get what? So I'm going to get it as S1 minus S naught over S naught. Actually, and I can, using this factor, I can show that this is equal to R. Okay. So R is what is returns on bonds, something deterministic, where there is no risk actually. While RS is what is a returns on stock actually, which is risky. So what this magical expectation is doing, okay, is basically turning something which is risky into risk-free. So therefore, you are saying that not risk, but it's neutralizing the risk. Okay, it's turning it into neutralizing the risk or something like this. But if you have such a good measure, okay, then how can I compute the derivative, which was the key question actually. Okay, so we said that there are two ways to price the derivatives at time 0. Number one, through replicating portfolio. Try to find a portfolio which can attain the value of the derivative at time 1, and then using that portfolio, just simply compute the value of that portfolio at time 0. You're going to get the value of the derivative at time 0, and that is going to allow you to hedge the risk. And the second way is to basically use this probability measure and try to compute the value of the derivative. And we can do it very easily. How we can do it? So I know, imagine I have a replicating portfolio. In other words, I have a portfolio X and Y. In other words, I have investing strategy in bonds and stocks, underlying asset, such that it agrees with omega, it agrees with, my derivative in which I am interested in. Imagine I have this kind of. Okay, if this is the case, then I can say that, okay, I'm going to have x b1 plus y s1 of omega, which is same as omega explicitly. And then I can discount it. So if I'm discounting it here, I need to discount it here as well. And I need to discount. So in other words, I need to divide both sides by 1 plus r. So if I divide this value by 1 plus r, this is going to turn out to be what? And then apply the risk neutral expectation on both sides. Okay. You are applying risk neutral expectation. You're going to be omega independent actually, because expectation does not depend on one omega, but depends on omega. Okay. So roughly this. So what is going to be the risk neutral expectation? This is going to be xp naught plus y, an expectation of s1, which is same as s naught. Expectation of stock value. Okay. What this guy is nothing but
B naught.
yeah, that's y. In other words, y, I can price it, by simply computing the risk neutral probability measure first, and then using that risk neutral probability measure, just simply compute